Hello students, in this session we will discuss topic column and strut. In previous session we discussed introduction of column and strut and we discussed what is crippling load and what is crushing load. We also discussed Euler's formula and Rankine's formula for calculating crushing and crippling load. We also discussed effective length of the column under different column conditions. Now, in this session, we will discuss Euler's formula in detail and we will also solve few numericals. Now, in this session, we will start with assumption of Euler's formula and then we will discuss limitations of Euler's formula. After that, we will derive Euler's formula for column when both the ends of the column are hinged. After that, we will solve a numerical. Okay. So, let's start with what is Euler's formula. So, here is the Euler's formula which is used for calculating crippling load. Euler's formula is applicable to long column only. And Euler's formula PE is equal to pi square EI upon LE square, where PE is Euler's crippling load, E is modulus of elasticity, I is moment of inertia and LE is effective length of the column. Now, let's discuss assumptions of Euler's formula. It means whenever we are applying Euler's formula for calculating crippling load, we made certain assumptions. So here, let's discuss various assumptions. Here is assumption number 1. So we assume that the material of the column is elastic, homogeneous and isotropic and Hooke's law is valid. Now in second assumption, we assume that the column is long and cross section of the column is uniform throughout its length. In third assumption, we assume that the column is straight before application of load. In fourth, we assume that the load on the column is truly axial. It means the load for which the column is subjected, line of action of that load is passing through the axis of this column. Now, this is the fifth assumption that the shortening of the column due to axial compressive load is neglected. So, whenever the column section is subjected to axial compressive load, shortening of column may happen. But we neglect shortening of the column. Now, this is the last assumption, which failure of the column is due to buckling. Okay, means here we apply Euler's formula for long column, and for long column we assume here that the failure of the column is only due to buckling. There is no crushing. Okay, so these are the assumptions that we made for applying Euler's formula. Now let's move to limitation of Euler's formula. So here is Euler's formula. Okay, as we discussed, P is equal to pi square EI upon LE square. Now we know that I is equal to what? AK square. So if I put I is equal to AK square in this equation, then P is equal to pi square E AK square upon LE square. Now I can rearrange the equation as P by A is equal to pi square E upon L by K square. Okay. Now we know that LE by K is lambda and P by A is sigma. So if I put sigma is equal to P by A and lambda is equal to LE by K in this equation, then the equation will be sigma is equal to pi square E upon lambda square. So I can say that lambda square is equal to pi square E upon sigma. Okay. Now let us discuss case of mild steel. So for mild steel, sigma is equal to 200 Newton per mm square. This is the proportional limit stress. Okay. Now E for the mild steel, which is Young's modulus of elasticity for mild steel, is 2 into 10 raised to 5 Newton per mm square. So if we put sigma and E value in this equation, then I will get lambda square is equal to pi square 2 into 10 raised to 5 upon 200. So I am getting lambda is equal to 99.34 So we can say that lambda is equal to 100. It means that Euler's formula is only applicable when lambda is greater than 100. Okay, so in other words, we can say that Euler's formula cannot be applied in case of short column. Okay, so this is the limitation of Euler's formula. Now let's move to the next topic, and here we will derive Euler's formula for column when both the end of the column are hinged. So in this figure you can see that the column has hinge end at both the ends A and B. And the column is subjected to axial load P, and because of this axial load the column will bend like this. Okay, y is the distance here I denoted. Okay, now the bending moment at the section is given by, so I am taking section suppose at a distance x from point B, then the bending moment m at this section will be minus load into distance. So here load is P and distance is y. So I can say that moment m is equal to minus P into y. Now let's apply differential equation for elastic curve. So it will be EI into d square y upon dx square, which is equal to minus Py. So we can say that EI d square y upon dx square plus Py is equal to 0. And the solution of this equation is y is equal to C1 cos under root P upon EI plus C2 sin under root P upon EI into x. Suppose the equation is equation A. Okay, here C1 and C2 are the integration constant. Now let's apply one condition. So when x is equal to 0, so you can see here in this figure at point B, x is equal to 0. Then y is also 0. Okay, and if we put x is equal to 0 and y is equal to 0 in equation A, then we will get C1 is equal to 0. Now let's apply second condition. So when x is equal to L, so you can see when x is equal to L, we reach to point A. Okay, so when x is equal to L, y is equal to 0. Then if we put x is equal to L and y is equal to 0 in equation A, then we will get C2 sin under root P by EI into L is equal to 0. Okay, so we can say that for this equation to be correct, C2 can be 0. Okay, so if C2 is 0, then there is no bending. It is not possible. So in other case, sin under root P upon EI into L should be 0. Now it is only possible when L into under root P upon EI is either 0 or pi or 2 pi or 3 pi as well. So let's take less significant case. So here I am taking L under root P upon EI is equal to pi. Okay, so I can write it down as under root P upon EI is equal to pi upon L. So P upon EI is equal to pi square upon L square. So I can say that P is equal to pi square EI upon L square, where L is the original length of the column. Okay, so this is the Euler's formula which we can use for the column with both the end as hinged. Okay, now let's move to our next topic. So here we will discuss Euler's formula for different column end conditions. In previous session we discussed effective length of the column under various column end conditions, and here we will discuss Euler's formula for various column end conditions. So here is the Euler's formula. Okay, now let's discuss case number 1. So in this case, let us take both the end of the column are hinged. Okay, and in this case we know that effective length of the column LE is equal to L. So if we put LE is equal to L in Euler's formula, then I am getting Euler's formula for the column, both the end of the column hinged, is equal to pi square EI upon L square. So here LE is equal to L, so the equation remains same. Now let's take second case. Here both the end of the column are fixed, and we know that for such condition effective length is equal to L by 2, where L is the original length. So if I replace LE is equal to L by 2 here, then I am getting Euler's formula for both the end of column fixed is equal to 4 pi square EI upon L square. Now let's move to third case. In this case, one end is fixed and other end is hinged. So we are discussing column with the one end fixed and other end hinged. And we know that effective length of such column is equal to L upon under root 2. So I am putting L upon under root instead of LE in Euler's formula. Then I am getting Euler's formula for the column one end fixed and other end hinged is equal to 2 pi square EI upon L square. Okay. Now let's discuss the last condition. Here one end of the column is fixed and other end is free. And in such condition LE is equal to 2L as we discussed in previous session. So here if I put LE is equal to 2L in Euler's formula, then I am getting Euler's formula for one end fixed and other end free is equal to pi square EI upon 4L square. So all this formula which can use for solving numerical. Okay, so let's calculate numerical. So first of all we will read data. Here a column of size 150 mm by 200 mm is given. So width of the column is 150 mm and depth of the column is 200 mm. Length of the column is 6 meter. It means original length L is equal to 6 meter and I am converting length into mm. So I am getting L is equal to 6000 mm. Now one end of the column is fixed and other end is hinged. So here column end condition is given. We need to determine crippling load and safe load both. Here factor of safety FOS is given equal to 3 and Young's modulus of elasticity E is also given. It is 17.5 into 10 raised to 3 Newton per mm square. Okay. So here is the formula, Euler's formula, which we will use to calculate crippling load. Okay. So let's start solving this numerical. Here column end condition is already given. So one end of the column is fixed and other end is hinged. And we know that for such kind of the column, effective length LE is equal to L under root 2. Original length of this column is 6000. So 6000 divided by under root 2, which is equal to 4242.64 mm. Okay. Now let's calculate Ixx first. So for the rectangular section, Ixx is equal to BD cube by 12. Value of B is 150 and value of D is 200. So I am getting Ixx is equal to 100 into 10 raised to 6 mm raised to 4. Now we also need to calculate Iyy. So equation to calculate Iyy for a rectangular section is dB cube by 12. Value of D is 200 and B is 150. So I am getting Iyy is equal to 56.25 into 10 raised to 6 mm raised to 4. So here I have calculated Ixx and Iyy both. But for the formula I need only one. So whenever such condition occur, we will calculate Ixx and Iyy both and we will take minimum value of I for the calculation purpose. So here value of Iyy I am getting less, so I am taking I for the equation is equal to 56.25 into 10 raised to 6 mm raised to 4. Now let's put value of LE, I and E in equation PE, so we will get crippling load. Crippling load PE is equal to pi square EI upon LE square. Here value of E which is given 17.5 into 10 raised to 3. Value of I that we calculated 56.25 into 10 raised to 6. LE we calculated it is 4242.64. So if I put all the values and calculate, then I am getting PE is equal to 5,39,744.16 Newton, and I am converting Newton into kilonewton. So I am getting crippling load is equal to 539.74 kilonewton. Now we also need to calculate safe load, and for that factor of safety is given which is 3. So safe load P safe is equal to PE upon factor of safety. PE as we calculated it is 539.74 divided by factor of safety 3. So I am getting P safe is equal to 179.91 kilonewton. So this is end of this calculation, means this numerical. Now let's calculate one more numerical. Okay, so here a hollow cast iron section having external diameter 250 mm and thickness 25 mm is used as 4.5 meter long column. Okay, so here dimension of the column are given and the column section is circular hollow section. Okay, so the external diameter D is 250 mm and thickness is 25 mm. So internal diameter will be 200 mm. Okay, now the column has both the end fixed. Here it is mentioned both the end of the column are fixed. We need to find out safe crippling load by Euler's formula. Okay, so here is the formula that we will use for calculating our numerical. Okay, so first of all here column end condition is given, and for both the end of the column fixed, effective length of the column LE is equal to L by 2. Now length of the column is 4500 by 2, so I am getting LE is equal to 2250 mm. Now let's calculate I. For the circular section, IXX and IYY both are equal, so I for the hollow circular section is equal to pi by 64 capital D raised to 4 minus small d raised to 4. So if we put capital D is equal to 250 and small d is equal to 200, then I am getting I is equal to 133.2 into 10 raised to 6 mm raised to 4. Now let's put value of E, LE and I in Euler's equation to calculate crippling load. So here PE is equal to pi square EI upon LE square. Value of E which is given 0.14 into 10 raised to 5. Value of I that we calculated 113.20 into 10 raised to 6. And value of LE as we calculated it is 2250. So I am getting PE is equal to 30,89,649.19 Newton, and I am converting it into kilonewton. So I am getting 3089.649 kilonewton. Now we also need to calculate safe load, and safe load P safe is equal to PE upon FOS. So PE as we calculated it is 3089.649 and factor of safety is 3.5. So I am getting P safe is equal to 882.75 kilonewton. Okay. So this is end of this session. Thank you.